In the first class on characteristic function, we have learned the definition of characteristic function, some elementary properties, but very basic properties of this characteristic function. And since it is defined using, or it is defined in association with a distribution function of a random variable, so natural question is it possible to explore this function more in terms of distribution functions, or is it possible to see some of the properties of distribution functions or some results relating to distribution functions from the angle of characteristic functions, or the other way around. So, today we will be discussing such a thing. Before that, we will first define what is known as convolution of two distribution functions, and we will see how this convolution of two distribution functions is related to the characteristic functions or can be characterized through a characteristic function. We will also discuss some examples of characteristic functions of different random variables, and I will explain two very interesting characteristic functions corresponding to two different distributions. So, characteristic functions 2. From the last class where we have defined characteristic functions, we have also studied how it is related or it is defined using a distribution function of a random variable. We have studied some very basic properties of these characteristic functions, and also some another interesting result, that how we can generate a characteristic function given a number of characteristic functions corresponding to a number of random variables. So, today we will just continue to discuss the same thing on characteristic functions, but before that, if you remember, in the last class we have introduced something that is related to sum of two random variables. That means, we have tried to explain or try to define or develop a characteristic function corresponding to the sum of two independent random variables or sum of two independent symmetric random variables, and we have seen that the sum is also symmetric. Now, in continuation to that, let me define what is known as convolution. The convolution of two distribution functions f and g is defined as another function capital H x, which is denoted as capital F star g of x, and is given by the integral minus infinity to infinity f capital F of x minus y into d capital G of y. So, this is similar to the Riemann-Stieltjes integral of capital F with respect to dgy or the extension of that. Now, the question is, what about this is a general form or general definition of convolution of two distribution functions. Now, this will reduce to, in case of a discrete random variable, that means when we are dealing with two random variables having distribution functions capital F and capital G, but these two variables are discrete in nature, then this integral boils down to just summation. So, capital H x equals to summation 0 less than n less than equals to x, summation x k equals to 0 to n p k q n minus k, where capital F x is nothing but sum over p k, sum over k lies between 0 to 0 less than k less than equals to x, g x capital G x is summation g n 0 less than n less than equals to x, and p k is nothing but the probability that x takes the value k, and g n is the probability that y takes the value n. Q j is probability capital Y greater than j. So, in using these expressions of capital F, capital G and other expressions in terms of P, G and Q, we can get the expression for the convolution of two distribution functions of capital F and capital G, and we denote this by H, which is nothing but the discrete convolution of two random variables. That means, convolution of two discrete random variables having PMF, PK and GN. So, one remark or a note is that if we have two random variables x and y with corresponding distribution functions capital F and capital G, then the convolution can be interpreted as the distribution function of capital Z, which is defined as the sum of two random variables, that is z equals to x plus y if x and y are independent. That means, from here we can immediately get the distribution function of the sum of two independent random variables using the individual distribution functions. Some other remarks: if capital F and capital G are distribution functions, then H can be proved that H is also a distribution function, which is convolution of F and G. This convolution is commutative in nature. That means, if you convolute G with F, what you get is exactly same if you convolute F with G. This comes from the very definition of convolution. Just a straightforward algebra, we can get this commutative property. This convolution, it's interesting to note that this convolution is also associative in nature. That means, if F, G and H are distribution functions, then convolution, first take the convolution of F and G, and then with that you take the convolution of that F star G with H, which is same as if you first take convolution of G and H and then consider the convolution of F with this G star H. So, whatever you do, you will get the same thing. So, this is known as associative property, and naturally one is interested to know, if we have already discussed the discrete setup, discrete scenario of convolution. Now, what happened, or can we define something analogous to probability density from this convolution? The answer is yes. If f is the small f is the density of capital F, that means capital F must be absolutely continuous in nature. Then capital F star G is also absolutely continuous, and the density is given by Hx equals to minus infinity to infinity f of x minus y into d capital G of y. So, this is a very important result, or maybe treated as a theorem, that we can generate the density provided it should be an absolutely continuous variable. Now, the convolution theorem. This theorem basically states or discusses the relation with the characteristic function. That means, rather how to define a characteristic function of the convolution of two random variables. That means, z equals to x plus y. So, how to determine the characteristic function of z when we know the characteristic function of x and characteristic function of y, provided x and y are independent random variables. The proof follows by the Stieltjes integral. So, just consider the partition a equals to z1 upper bracket n less than z2 upper bracket n and so on, and the last point z n plus 1 upper bracket n equals to b. That means, we introduce n plus 1 points to get the partition, and just consider the Stieltjes integral, or write the characteristic function of z as a Stieltjes integral. So, minus infinity to infinity to the power I t z d h z, which is nothing but the limit of this entire sum. Here the function is nothing but e to the power I t z. So, e to the power I t z j upper bracket n into h z j plus 1 minus h z j. So, this is just by the definition of Stieltjes integral, which is equals to, we can immediately write this summation of this quantity z j minus z j upper bracket n minus x, and we integrate this entire quantity by e to the power I t x into d g x. Now, that means basically we are introducing this x inside. That means, we multiply this quantity by e to the power minus t x, and we adjust it with e to the power I t x. And so, what is this x? X should run for every x belonging to this real line. So, if you look at this entire expression and consider the limit, then this quantity would be the integral of e to the power say I t y a minus x to b minus x d of f y. That means, just by putting z minus x equals to y, we will get this expression. And since we are considering the partition a to b, this converges to the integral a to b, and after transforming the variable z minus x equals to y, we will get this inner integral as a minus x to b minus x integral e to the power I t y into d f y, and the whole thing multiplied by e to the power I t x and this integral with respect to g x. Now, just take let a goes to minus infinity and b goes to infinity, we immediately have phi of zt equals to nothing but phi of xt into phi of yt. That is, if we consider the convolution of two random variables, or rather two independent random variables, then the characteristic function is nothing but the product of the characteristic function of two independent random variables. Let us consider some examples of characteristic functions. So, if x follows binomial with parameter n and p, then phi t is x equals to 0 to n expectation of e to the power itx, which is nothing but x equals to 0 to n e to the power itx n cx p to the power x into q to the power n minus x, which actually if we just consider this sum, this boils down to q plus p into e to the power it whole to the power n. Exactly similarly, we can get the characteristic function of a Poisson random variable with parameter lambda, which incidentally small phi t equals to this expression, which is equals to e to the power minus lambda into 1 minus it. Now consider the famous distribution, which is nothing but the normal distribution with mean mu and variance sigma square. So, if x follows normal mu sigma square, then after a little bit of calculus and algebra, we can see that phi t is equals to e to the power I t mu minus t square sigma square t square by 2. And if x follows gamma with parameter lambda and theta, then small phi t equals to 1 minus I t by theta into whole to the power minus lambda, provided theta and lambda greater than equals to 0. So, these are just some examples to give you some flavor of how this characteristic function really looks like corresponding to a random variable. So, these are the very standard distributions, and for those distributions we have derived the characteristic functions of those distributions. Now, two very interesting characteristic functions I would like to mention. First, consider a Laplace density, which is f x equals to half into e to the power minus mod x. X lies between 0 to infinity, and it can be shown that if we consider the characteristic function, this characteristic function is nothing but 1 by 1 plus t square. Now, this obviously triggers some known form of one thing, which is nothing but PDF of another random variable, which is nothing but the Cauchy distribution or Cauchy density. If we just write the density function of Cauchy random variable, then f x equals to 1 by 1 plus x squared. And if we calculate or derive the characteristic function of this Cauchy random variable, we will see phi t equals to half of e to the power minus mod p. So, you see the density function of Cauchy is nothing but is exactly in the form of characteristic function of Laplace density. On the other hand, the Laplace density function is in the form of the characteristic function of Cauchy density. So, there is some relation, some interesting feature can be noted based on these two distributions. So, characteristic function of one variable is the density of the other variable, rather the form of characteristic function of one variable is the form of the density function of another variable. Now, the question is it possible to get moments from the characteristic functions of a random variable, provided the moments exist? And there is a very famous theorem that if phi t is the characteristic function of a distribution function capital F has derivative of order k at t equals to 0, then all moments of capital F up to order k exists if k is even and up to k minus 1 if k is odd. Conversely, if the moment alpha k of order k of a distribution function f x exists, then the characteristic function phi t can be differentiated k times, and in fact we can have this result phi k times derivative kth derivative of phi t is nothing but I to the power k integration minus infinity to infinity e to the power I t x dfx, and alpha k, that is the kth order moment, can be given as I to the power minus k kth derivative of phi at t equals to 0. So, this theorem basically gives us the moments from a characteristic functions, and just consequence we can put another theorem that if f x is a distribution function and we assume that nth derivative exists for different values of n, then the characteristic function of phi t of capital F admits the expansion, that is small phi of t equals to summation j equals to 0 to infinity alpha j I t to the power j by j factorial plus some term which is very negligible or which goes to 0 as n goes to infinity. So, it admits the expansion from which we can get the moments up to nth order if the nth derivative exists. So, basically this gives us one interesting theorem which relates the moments with the characteristic function of a distribution function, and it will actually immediately give you the moments irrespective of, we do not need to know that up to what order moment exists. It will immediately tell us automatically that, well, since nth derivative up to nth derivative exists, then you should get moments up to order n and so on. So, this is n is any integer. So, this gives us a result that relates characteristic function with the moments of a distribution function if the moments exist. So, today we have explored some more properties or some more theorems on characteristic functions in relation to the distribution functions, or rather more than one distribution functions of more than one random variables. We discussed some examples of characteristic function of very standard distributions. Another interesting thing that we have introduced, and in terms of theorems, although without proof, that how moments are related to a characteristic functions, or how moments of a distribution can be generated from a characteristic function provided the moments exist. So, these are all some of the nice properties of characteristic function which we have already explored. These properties or these theorems and results will be used to explore further this area, this very broad area on characteristic functions in relation to some of the limit theorems in probability as related to distribution functions, some more different types of convergences that we will be discussing later.